Welcome to this lecture. So as before, let's quickly recall what we have done so far. So in this week, we have been looking at the measure subsets, which allows us to look at how likely certain events are in some random experiment, or how large or important is one subsets, some certain subsets in your measurable space. So far we have studied many examples of such measures, and in particular probability measures, and we have also looked at many interesting properties of measures which we called as algebraic properties, involving many inequalities or equalities and involving usual algebraic operations like addition and subtraction. Now in this lecture we start looking at certain continuity properties of these measures. So let us start by moving on to the slides. So in the previous lecture we have discussed these algebraic properties. Now we start by looking at a slightly different type of properties. So as before, let's fix the notation first. Omega f mu is a measure space. So here mu is a measure on the measurable space omega script f. Now what we are interested in are limiting behaviors of this measure. What do I mean by that? We look at this quantity. Since a measure mu is a function defined on this sigma fields, some collection of subsets, then we can take sequences of sets an and look at the corresponding sizes or measures of these sets, which is mu of ans. So original collection, original sequence that was there, that was from the sigma field, and now correspondingly we are looking at the sizes of the sets, and that allows us to construct a sequence of non-negative numbers, which of course could be infinity, which of course could include infinity. Now we are interested in the limit values of these measures of an. Okay. Now these type of results may also be thought of as continuity properties of mu, since we have already discussed certain limiting notions for the sets an. So therefore we would like to connect the notions of limits of the sets an with the notions of limit of mu of ans, and that's why we are going to think of all these properties as continuity properties of mu or limiting behaviors of mu. So in this regard, so this is the result we are going to study. Continuity properties. The first part says that a measure mu is continuous from below. What is this? It's like this. So take an increasing sequence of sets an and call the complete union, call the countable union of ans as capital A. This is the usual notation used earlier. Then we claim that measure of ans increase and increase to this limit value, which is nothing but the measure of A. So this is continuity from below. So if an increase to the set A, then measures of an also increase to the measure of A. So that's the continuity property. The second property says it's also continuous from above, but with certain restrictions. What is this? We start with a decreasing sequence of sets going down to the complete intersection, going down to the countable intersection, which we have used. This notation we have used earlier. So A denotes the countable intersections of an. Now we have this additional condition that at least one of the sets ak should have finite mass. Now remember, we are dealing with a general measure, so measures of an could be infinity. The sequence that you have taken may have infinite sizes. The sequence of sets that you have taken may have infinite sizes. What we want is that at least one of the sets should have finite mass. Then we claim that this limit also holds, that measures of an decrease to the measure of A. So if ans decrease to A, then measures of an decrease to measure of A. So now just to quickly clarify, here in the statement it's written in terms of a limit, so that is the second part again, and in the first part it's also in terms of the limit, but I have mentioned that this is a increasing limit, these measures increase here, and in the second part the measures decrease here. So why is that? It is because of the fact that when you are looking at an increasing sequence of sets, then by the monotonicity property that was proved in the previous, that was discussed in the previous lecture, we have measures of an must increase. Similarly, if ans are decreasing, then measures of an must decrease. This is again by the monotonicity properties that was discussed in the previous lecture. Using that, we are now going to continue and talk about the actual limit value. So, for the first part, there was no restriction. We are going to consider increasing sequence of sets an, and we are going to show that measure of ans increase to measure of a. But here for simplicity, we split it into two parts. First, assume that measure of ak is infinity for some k. Okay. So, if it so happens that measure of ak is infinity for some k, then since ak plus 1 already contains ak, then by the monotonicity property that was proved in proposition 7, you immediately claim that measure of ak plus 1 is also infinity, because measure of ak plus 1 must be at least measure of ak, and measure of ak is taken to be infinity as per the assumption here. Likewise, you can repeat this argument and claim that measures of an is infinity for all n greater or equals to k, because these sets are increasing. So, if one of the sets has infinite mass, then all the next sets will also have infinite mass. But then what happens to the limit value? The limit value is nothing but infinity. So, limit of measures of an is infinity. But on the other hand, if you are looking at the complete union, ans are contained in A, the complete union. Now, measure of A must also be infinity because it contains the set ak. Therefore, measure of A is also infinity. Thus, the required equality holds, because the limit value is infinity and measure of A is also infinity. Now, in the second part, now we look at the other case. So, in the first case, we assume that one of the sets has infinite mass. But now you assume the contrary, the opposite condition, that all the sets has finite mass. So, this is the interesting case. So, if all the sets has finite mass, now look at the complete union A once more, but then you apply your familiar disjointification. So, you construct these sets B1, B2, Bn, but since these sets Ans are increasing, you can actually simplify it and write it using this pairwise disjoint union. So, this construction was done earlier, but for the special case of increasing sequences, you get this decomposition. What is this? So, the complete unions of A is nothing but first A1, then A2 minus A1, then A3 minus A2, and so on. So, earlier recall it was like A1, then A2 minus A1, but the third set was A3 minus the union of A1 and A2. But since the sets are increasing, union of A1 and A2 is nothing but A2 itself. That's why you get this simplified relation. Therefore, so by this earlier construction, these sets A1, A2 minus A1, and so on, these are pairwise disjoint. So you would like to apply now the countable additivity of the measure. But then note that by the corollary of the proposition 7 that we have discussed again by the monotonicity properties, you also have this relation that measures of this thing an plus 1 minus an is nothing but this subtraction. This is also true. This is true because of these two reasons. First, an plus 1 is the disjoint union of an and an plus 1 minus an. Just to repeat, an plus 1 is the disjoint union of an and an plus 1 minus an. So, you have these two sets pairwise disjoint. Apply finite additivity, you get that measure of an plus 1 is nothing but the addition of the individual sizes of an and an plus 1 minus an. But then, since you are dealing with sets with finite mass, we have made that assumption, you are allowed to subtract and get this relation that mu of the measure of an plus 1 minus an, that is on your left hand side, is equal to measure of an plus 1 minus measure of an. Okay. So, now all you have to do of the countable additivity of the measure mu on this complete union A. Since you have written it as a countable disjoint union, what you get is that you get this relation that measure of A is nothing but the addition of all these measures, additions of these sizes. But then you have proved that measure of an plus 1 minus an is obtained by subtracting measure of an from measure of an plus 1. Now look at this series. This series has the partial sum given by measure of an plus summation from n equal to 1 to m of this telescopic sums. If you are looking at the mth partial sum of this series, you will simply get mu of a1 plus summation n equal to 1 to m of this thing. But then for the finite sum, you can easily compute that this becomes a telescopic sum, many of the terms cancel off, and the remaining term is measure of a n plus 1. But since this countable additivity holds, you are basically saying that measure of a is nothing but the limit of this series or the summation of the series, but that is nothing but the limit of the partial sums. But the partial sums themselves are nothing but measures of a n plus 1, and therefore you immediately get that measure of a is nothing but the limit of partial sums, which is nothing but this quantity. So here we have used the fact that a series is equal to the limit, the series value is equal to the limit of the partial sums, and that allows us to claim this equality. Okay, so that proves the case when the sets are increasing. But when the sets are decreasing, you also have that assumption that there is at least one set ak for which the measure is finite. So you start with that. Then observe this, that the sets ak minus an, so here you fix k and vary n. You look at these sets ak minus an. Since ans are decreasing, you will get that ak minus ans will increase and increases to ak minus the complete intersection capital A. But then here you can apply the first part, because this sequence now is an increasing sequence. So if you apply that, then measure of ak minus a, that is the limit value of the measures of ak minus an as n goes to infinity. But then since you are dealing with sets with finite mass, since ak you have finite mass, then ak minus an also has finite mass. Then you can rewrite this equation equality as measure of ak minus measure of a, because a was a subset of ak, so measure of a is also finite. So you can write the left hand side as the difference of measure of ak minus measure of a. On the right hand side, again you apply the same fact, since measure of ak is finite, measure of ak minus an is also finite, and you can write it as a subtraction of these quantities. Therefore you get this relation. But then measure of ak is finite, so you can cancel off measure of ak from both sides and the required result follows. So you get limit of measures of an is nothing but measure of a. But this is using the fact that at least one of the sets has finite mass. But now we are going to ask that what happens if you are considering a decreasing sequence and all of the sets has infinite mass. What happens there? So for this case there are counter examples. So now if you are dealing with finite measures, then this condition is automatically satisfied, so you don't have to worry about it. So in particular for probability measures, this condition is automatically satisfied. So therefore what you actually have proved from that proposition is the fact that finite measures, including probability measures, are both continuous from above and continuous from below. Okay, so take any increasing sequences or decreasing sequences, then the appropriate limit holds. So that is what I mean by continuous from above and continuous from below. So for finite measures and in particular for probability measures, you have this fact. But then for an infinite measure, you can find examples where all the measures of the sets that you are considering have infinite mass. The sets decrease to that countable intersection, and then you can try to show that measure of a is not equal to this. So you have to construct such an example explicitly. Please work this out. Okay, so this will give you a counter example to the fact that when there are infinite measures, there can be some sequences which are decreasing, but the equality does not hold. So the measure need not be continuous from above in that cases. So please work out, please find such an example. Alright, now we restrict our attention to a familiar collection that was considered earlier in the previous lecture. What is this? So consider two probability measures P1 and P2 and look back at the collection of subsets where the probabilities match. So probability of A under P1 and P2 must be the same. So look at those special subsets and call that collection as script epsilon. Earlier we had proved that this collection is non-empty and closed under complementation, finite disjoint unions and countable disjoint unions. Now we are going to show that this collection also has some nice structures, like that this is a monotone class. How do you show this? So to show this, all you have to verify that this collection script epsilon is closed under countable increasing unions and countable decreasing intersections. How do you show this? So let's check the first conditions. So take a increasing sequence an with A being the union. Then if ANs are already in this collection, you would like to show that the union is in the collection script epsilon. Now you observe that if ANs are already in this collection, then the probability of ANs according to P1 and P2 must match. We want to show that the probability of A, the union, must match under P1 and P2. To show this, you apply continuity from below. Why? If the sets ANs increase to the set A, then by the continuity from below of the probability measure P1, you get that probability of P1 of A is equal to limit of P1 of ANs. That was just proved as continuity from below. But then if P1 of AN is nothing but P2 of AN, you rewrite it in terms of P2, and here you apply the continuity from below of the probability measure P2, and you end up having the probability of A in terms of P2. So therefore the union has the same probability under P1 and P2. So hence script T is closed under countable increasing unions. And a similar argument involving the continuity from above for this probability measure P1 and P2 will show you that it's also closed under countable decreasing intersections, and hence script T is a monotone class. But here for the increasing countable decreasing intersections, what you have to use is the continuity from above, and just note that any finite measures, in particular for probability measures, this property is true. Okay, so for any probability measure, it is continuous from above and continuous from below. So this is what implies that this collection script T is closed under countable increasing unions and countable decreasing intersections, and hence it becomes a monotone class. Okay, we now consider a concept related to increasingness and decreasingness of sequences of sets. So a measure mu on a measurable space omega script f is said to be sigma finite if you have a sequence of sets omega n increasing to omega, and this omega n first of all must be from your collection, from your sigma field, and with the additional condition that measures of omega n are finite. So again we are considering measures on some measurable space. We would like to figure out a increasing sequence of subsets omega n such that omega n's have finite mass, but omega n's increase to omega. Okay, so in this case we are going to say that omega f mu is a sigma finite measure space. All right, now a quick clarification. Here we are not saying anything about the measure of omega. We are only restricting that measures of omega n's, those special subsets that you consider, must have finite mass. So if there exists one sequence omega n like that, if there exists a increasing sequence omega n like that, then you get that the measure, you say that the measure is sigma finite, and call the corresponding measure space as sigma finite measure space. But again, you are not saying anything about the measure of omega. It could be finite, it could be infinite. Okay, so let's first understand what are some examples. So if you look at a finite measure, then of course you can take omega n's to be omega itself. So it's a constant sequence of sets. So all the sets are omega. These are of course subsets as per our definition, and each of which has finite mass because we have taken a finite measure. So therefore you get an increasing sequence of sets, and you get that these finite measures are sigma finite. In particular, all probability measures are sigma finite. Okay, but then you would like to get examples for the case of infinite measures. So an infinite measure which is sigma finite is discussed here. So consider the measurable space of integers of natural numbers n and the corresponding power set. So look at the measurable space given by the, consider the measurable space with the set of non-negative set of natural numbers with the power set. Here consider the counting measure. So here the set of natural numbers is countable. So therefore set of natural numbers is countably infinite. So the number of elements there is infinite. So mu of n, the size of the set n is infinite. So that is already given to us. So this is an infinite measure. But then consider the sets omega n, which is like this 1, 2 up to n. So it has exactly n elements omega n for each n. Then look at the union. The union is nothing but the set of natural numbers. But then omega n is contained in omega n plus 1, because omega n plus 1 is the collection 1 to n up to n, 1, 2 up to n and n plus 1. So therefore omega n is contained in omega n plus 1, and their union is nothing but the set of natural numbers. But here observe that number of elements in omega n is nothing but n itself, which is finite. So it is finite for each n, but mu of omega is infinite, and here you end up having an example of an infinite measure which is sigma finite. So you get these pieces omega n where the sizes are finite, but the sets increase to the whole set and gives you the example of a sigma finite measure. But it's a word of caution that not all infinite measures are sigma finite. But in this course we are not going to consider such measures. We are not going to consider any infinite measure which is not sigma finite. We are not going to consider such measures. But we are going to consider sigma finite measures on the real line, and these will be some very interesting examples which of course includes probability measures on the real line. So this we are going to see in later lectures. We stop here and we are going to continue the discussions about properties of measures in the next lecture.